let's get started. Good morning and welcome back from the break. Hope you all had a good week, whether you're here or elsewhere. Today we're going to start to talk about synthesis. Particularly, we'll have an overview of ways that nanostructures are made, and then we'll talk quantitatively about the kinetics of nucleation, or the first step to synthesis of small structures. First, I just want to ask if there are any questions about the project or the video assignment. Okay, and then your video assignment is due next Monday. I'll be sending out a notice with details on how we're going to upload those, like to YouTube or something. Try to have a group site for that.
I think it said online that it was due this Friday. Is that changed to Sunday?
So that's changed, and I may have forgotten to update the due date, but I pushed it ahead to Monday because the exam got pushed ahead of us all. So I'm thinking I forgot to update the document before the break. And also the homework 3 is due next Wednesday. So this is the kind of propagation of due dates forward a bit that I discussed at the beginning of the last lecture before the break. And the syllabus has been updated to reflect that. Okay. So last time we talked about this general approach of top-down versus bottom-up methods of fabrication. And this is just a schematic summary that shows the idea that by top-down methods such as lithography, we've been able to take materials apart at smaller and smaller feature sizes with higher and higher resolution. And this is what has driven a lot of the integrated circuit industry for manufacturing of things like computer chips and microelectromechanical devices. And the alternative approach is what people call a bottom-up method, where you take small pieces, could be as small as atoms, and put them together into ordered architectures. And I think the way nano manufacturing is going is an effective combination of top-down methods and bottom-up methods. So we need to understand how to make nanostructures and how to put them together and how to interface those with things like circuits and templates that can give order over larger length scales. And while there are a lot of examples, some of which we'll start to talk about today, of making nanostructures in bulk, making things like solutions of quantum dots, like the colored vials we've seen several times already, or large quantities of carbon nanotube powders. There are over 300 tons of nanotubes made every year around the world. We haven't yet really reached the full commercial realization of things that combine these top-down and bottom-up approaches. And back in the day when the first transistor was made, it was relatively large, something on the sort of tabletop scale. And now we're making transistors by optical lithography and advanced methods of lithography that are tens of nanometers in size. Yet the limits of these top-down methods don't quite approach the ultimate size of the nanostructures that we're going to talk about synthesizing. So, where we are right now is sort of deciding and pushing this crossover interface downward, where we can seek to interface individual structures or assemblies of small groups of structures with features made by top-down methods. And last time I concluded by mentioning this general approach to templating the position or assembly of nanostructures. And this slide sort of just generally showed the approach whereby you could use lithography. This, for example, could be e-beam lithography or advanced optical lithography to produce a trench that's 50 nanometers wide, or you could say conventional optical lithography on the higher end to produce something which is 5,000 nanometers or 5 microns wide. And upon this template, we could think about, in a general sense, how we would make nanostructures and use the template to enforce their assembly in an ordered configuration. And so we'll deal with the specific methods by which this is done later. We want to start thinking about how to create these small structures of controlled size. In these cases, these are polymer nanospheres. And in the upper case, what is going on is the authors are talking about the ability to use surface topography to control the de-wetting of thin film. So instead of having, for example, particles on a substrate that are essentially islands of metal, for example, if you have a topographically controlled substrate, it's energetically favorable for the islands to sit down in these cavities, and because of the interactions between the cavity and the metal, for the islands to be of similar sizes. So these are kind of just two general approaches toward combining the ability to create features from the top down with the ability to understand how materials evolve from the bottom up. And in the next few lectures, we'll talk about how to create structures in these categories, and we'll give some examples of how to start to interface them. for example, how to make the quantum dots that we've seen in the vials, how to make nanotubes and nanowires, and think about how their size distributions emerge and evolve, and then how to assemble things like structures of polymers. Block copolymers are one type of polymer nanostructure, or assemblies of colloidal particles, or you could think of these as clusters of nanoparticles sitting inside a solution or that are arranged on a substrate. And as we go through the portion of the course on synthesis and the portion of the course on assembly, I want to think about, start to keep in our minds a bunch of important considerations. For example, how do we control the process to determine the size of nanostructures and determine their size distribution? What are important issues of process compatibility, of chemistry and of temperature? For example, there's a big difference if you make your solution of structures in one step and then, say, try to assemble it on a surface or deposit it into another configuration versus an approach where you make the nanostructures in situ. For example, deposit them or grow them directly on a surface. That might require very high temperatures, or you may have to be concerned about the conditions of the chemical atmosphere for growing the structures in compatibility with the other things you have down, like, say, electrodes to contact your structures. And then at the levels of the structures and the levels of their interfaces, we want to think about how we may measure and control the defect density and the purity. The defect density being, for example, the flaws in the structures. For example, those 5-7 defects that we saw in carbon nanotubes that are means of propagating mechanical flaws and leading to propagation of strain. And if we say that defects are impurities in the structure themselves, or defect density is so mistakes in the structure themselves, we can also address the issue of purity. What other atoms that we don't want, or what, say, amorphous structures, amorphous carbon, say, on the sidewalls of carbon nanotubes we may have. We may want to think about the structure and profiles of interfaces with other materials. What is the contact resistance between a nanotube and its electrodes, and how does that relate to how the materials mix, or how you may post-process the structures to, say, anneal the contacts to lower the contact resistance. And in the cases of organization and assembly, there are all these kind of manufacturing-like terms where we're concerned about how specific are the interactions of the structures with each other. That may relate to getting, say, A and B to assemble and B and C to assemble, but not A and C to assemble together. And how do we control the alignment and the registry of the structures, the positioning and the orientation, for example. And we'll see cases where this is vital for growing the structures in place. Say you wanted to grow nanotubes across a trench or across a pair of electrodes, and, say, imposing an electric field during the growth process might be able to influence the structures. And it's also important if you employed the approach of making the nanostructures to the start, dispersing them in a solution, and then, say, depositing the solution, evaporating it or flowing it, and trying to influence the organization of the structures as well. And it gets back to, in my view, all this basic idea of controlling the accuracy and precision of the process. What is your size distribution, what is your error, and how broad is that distribution, and how do you control the conditions to make that, for example, as narrow as you want or as broad as you want. And we'll come back to the start and see the influences of those, say, breadth of size distribution on things like the optical properties of nanocrystals, of quantum dots. And that continues to be, I think, a very good example of how the process control can affect the properties directly. And in fact, there are very good models for understanding how the sizes of these structures evolve with time. And we'll use that as an example to maybe build some understanding or view toward more complex systems. So we're going to step through the synthesis methods for the building blocks that we outlined at the beginning of the term. And I've decided to kind of rearrange the way the subject is addressed compared to past years, and today introduce the idea of nucleation, or the initial step of formation, and then on Wednesday talk about the growth of nanoparticles, and that in the context of how the sizes evolve versus time. And then on Monday talk about specifically nanotubes and nanowires, and in that case introduce some examples of how the synthesis processes are integrated with top-down methods. But through this path, we'll talk about examples of how nanoclusters are made, nanoparticles are made, nanowires and nanotubes are made, and even how things like sheets such as graphene are made. And this is often a combination of some basic methods that are widely used in thin film deposition and processing. things like chemical vapor deposition or evaporation, with particular attention to the fundamental processes that happen. And there are, in fact, a lot of similarities from growth of bulk crystals to growth of nanoscale crystals, but now by examining the relationships between, say, how the nanowire grows and what its properties are, or how the atoms are incorporated at the interface here, is letting us really understand the fundamental mechanisms by which these structures are produced. And I like this cartoon from a while ago that shows a nanotechnology lab with all these little people coming out. And I don't know if they're working in the lab or if they're products of the lab, but maybe we could say the best way to make monodispersed structures is to employ a large number of small people, or to understand if we were all very little people and we were sitting and watching the structures grow, what are the key parameters that govern the process. And it's indeed really hard to characterize in some ways how the structures evolve, and things like in situ methods for measuring the temperature and the pressure in the system and relating those to how the distributions evolve are very important. And if we had a way of sitting right at the structure and counting the atoms arriving and knowing the local pressure and the local temperature, we would have a lot more understanding about this. But today we're going to think about more bulk models, say ensembled averages that consider all the structures being the same, and then those structures having, say, a prescribed size distribution. We'll think about how those sizes form and how those sizes evolve with time in the process. So today we're going to talk about a general overview of synthesis methods for nanoparticles, nanowires, and nanotubes. I'll try to give you some examples of how these different types of structures are made, how those relate to classical methods of thin film deposition, and how those uncover some interesting effects of how things happen from the bottom up. Because you could say that if you deposit a thin film by a bulk approach, where you're just, say, creating a vapor of a material in a chamber and putting something on a substrate, at the atomic level, you are in fact, causing a bottom-up process to happen. And now we have to pay special attention to how the atoms organize and how that organization relates to properties, and how we may change the conditions to, say, evolve nanostructures of different sizes and different types. And then in the latter half of the lecture, we'll go through a simple thermodynamic model of what we'll call homogeneous nucleation, or the idea of, say, having our room filled with a vapor and changing the conditions so it's favorable to nucleate clusters of that vapor. And that's perhaps the most basic view we can take on how we would create nanostructures. And that will be a springboard for, on Wednesday, studying the implications of this model of nucleation in nanoparticle synthesis, and studying how the size distributions of the nanoparticles will evolve versus time as we change the conditions. And then next Monday, we'll talk about implications and applications in nanotube and nanowire synthesis, some process examples, and how a lot of these processes are starting to be integrated with top-down methods and cases of device fabrication. And I hope there we'll start to see a connection between synthesis and properties, and a lot of the properties that we learned about in the first part of the course. And I've chosen to put all the readings for the next 3 lectures, today, Wednesday, and next Monday, up on CTools now. So let's step through this list quickly. The start for the quantitative parts of today and Wednesday are written notes that I'm going to post right after this lecture, and that's one PDF file that covers today and Wednesday. And then there's a paper from Sugimoto which talks about the theory behind the nucleation and growth of nanoparticles, or he calls the monodispersed colloidal particles in solution. And this is really a backup to the written notes I'll provide. I think that this is written in a bit more confusing way, but I wanted to provide it as the source where I got the material for my notes. And then the Peng paper talks about the practical application of what the top 2 points discuss. Basically, how synthesis of quantum dots is controlled to focus and broaden the size distributions, make the diameter distribution narrower and make it broader. And then in the second set down here, I have a set of papers that focus on nanowire and nanotube growth. Kotombaka's paper talks about the kinetics of individual nanowire growth as viewed in a TEM. And Hochbong talks about growth of vertical arrays of silicon nanowires and methods of patterning the catalyst and relating the size distribution of the particles to the size distribution of the wires. And then the last two papers by Terranova and Wirth talk about overviews of methodologies for growing carbon nanotubes and a study of the kinetics of growth of carbon nanotube films. And this Terranova paper gives some examples of apparatuses, types of reactors used to grow carbon nanotubes. And a lot of these are used to grow other types of structures, but I chose this as the example in which we'll look at different types of reactors that are used for these kinds of productions. And then in the extras category, this is a lot of reading as it is, so I don't intend you to look at any of the stuff on this slide, but I have a list of further papers that are broader reviews if you're interested in this topic for further research, as well as some very recent studies on pushing the limits of our understanding at the atomic level. For example, looking at how the atomic interface moves as a silicon nanowire grows, and for example, what determines the chirality of carbon nanotubes. I'll probably touch on these briefly next Monday, but this is more specific topics beyond the scope that we'll be responsible for, but they're provided for your reference in the extras folder. So if we think from the most basic level, how do we start to make nanostructures? When we start from nothing, the first thing we want to do is we want to nucleate them. So we want to go from, say, having a uniform distribution of atoms in the gas phase inside this room, and all of a sudden I want to instantly form small clusters of a certain size. And the process of nucleation, of course, refers to forming the nucleus, or what is the initial starting point of growing the structure larger. And then if I want to grow the structures, make them bigger, then I want to grow the structures so they become bigger. But there's an important difference whether I can control my process. So I nucleate and then I grow, where maybe in the first step I only nucleate, and in the second step I grow some of the initial nuclei bigger, but I form additional nuclei. And you can see here, now I'm starting to get, in this case I have two distinct sizes, but really I'd have a broad size distribution, a case where if I am simultaneously creating new structures and making older structures, older nuclei bigger, I kind of lose control pretty quickly. And this is an effective process to make small structures, but there's a decided difference between if I do this or if I first nucleate the structures and then I grow the structures, whereby after I turn the nucleation process off, I only add material to the existing structures rather than create new nuclei in the first place. So you could say that a primary strategy for controlling the size of these small structures is to have a process where, in the end you get an almost exact precision in the size, and in practice you have two separate events. You have a nucleation event and you have a growth event. You form nuclei of a certain size, you get the process started, and then you add to the previous nuclei to evolve the size the way you want. And this is the differences between this slide and the previous slide is the picture we'll try to paint quantitatively between today's material and Wednesday's material. And what we end up with here could be the final structure. For example, we could be making quantum dots in solution, and if we control the process as we wanted, we could have a green vial of quantum dots whose size determines a band gap that emits light in that wavelength range. If we didn't control it well, then we might end up with with a solution that doesn't have a precisely defined color, or has white light, or is white because it's a mixture of all colors. Likewise, we'll see later examples of maybe here I just made this one pink and this one blue to emphasize that this was the nucleus and this is the other growth, but they're all one material. But there are other cases in which we could, say, change the material that we're supplying, and this could actually be, say, one compound, and this could be another compound. And those kind of core shell structures might have other properties. Another thing that might be going on is we might need to make these particles and then use them for another process. So, for example, we might be making nanoparticles, which are then catalysts for growing nanowires or growing carbon nanotubes later. And we'll see how the distribution of these particle sizes can directly influence the size distribution of the nanowires or the nanotubes we could grow afterward. So from this basic picture, I think we can build a lot of connections to other more sophisticated processes and other and more sophisticated architectures. And there's no way we'll be able to get through all the possible examples or configurations, but the goal is to get kind of this qualitative understanding of what governs the nucleation and growth of nanostructures and what types of processes are used to make them, so we can think about what the capabilities and limitations might be and how we might design effective processes to control these key variables. So one of the most common ways that nanoparticles are made is in a liquid phase solution. And when we get to the end of the lecture next time, we'll talk a bit more about example chemistries for this process. But I wanted to show you this example now to illustrate the strategy for decoupling nucleation of structures from growth of structures. So a typical apparatus for making nanocrystals in solution might be, for example, a glass vial here, or a glass flask here, which is under controlled atmosphere. So, for example, contains no air. You can bring a purge gas in here. And it's, for example, sitting on a hot plate, so you can control temperature. And maybe that hot plate has a stirrer, so you have uniform circulation in the liquid. And you have, say, a thermometer, so you can control the temperature or know the temperature. That might be fed back to the hot plate. And you have a way of injecting a precursor solution. So the idea of being able to control the temperature and being able to control the concentration of the solution are two ways that we can change the conditions of the process over time. And the graph here, I'm sorry it's a bit blurry, is showing, for example, how the concentration of the precursors in the solution might vary versus time as this process proceeds. So it might be typical, for example, to start out just with a liquid solution, a solvent, in which this precursor is soluble, and not have any precursor in it. Turn on the hot plate to heat it up to, say, 300 C. And then when the temperature is stable, move the syringe and inject a certain amount of precursor in here, such that when it's stirred apart, it reaches a desired concentration. And if that concentration of the precursor now in the solution is above a certain critical concentration for nucleation, which we'll derive later, then it's energetically favorable for structures to nucleate, for our first slide to go from being blank to go having a whole bunch of little blue dots on it. And then the nucleation process, because nuclei form, if you don't add more precursor, that also drops the concentration of precursor in solution. And then different things can happen depending on what you want to do. But in the simplest case, that nucleation event would drop the concentration down, and then you may just grow additional structures. You may just grow the structures from those seeds you've created. So you'd go from having a nucleation event to a growth event, because the nucleation event drops the concentration below this critical threshold. And in practice, what you would do is you would also change the temperature versus time in ways we will see later to separate those nucleation and growth events. Basically try to maximize the energy difference between that case of nucleation and that case of growth. So you can rapidly create monodisperse nuclei, and then over time you can then grow larger and larger particles. And you can grow those particles with a controlled size, but you can also confine the size distribution. And the ideal case perhaps being that you grow the particles with time to give you your final size, say 5.5 nanometers, and through that growth process, as the particles get bigger, there are also ways that the process is controlled so they become more and more, have a narrow and narrower size distribution, so the standard deviation of the particles also remains bounded and remains as small as possible. In other conditions, which may not be what you want, you could imagine that as the size gets bigger, the size distribution also gets broader, and that in many cases is not what you want. And there are very well-known ways to control that in the case of this basic example. So this idea of having a supersaturated solution and nucleating structures from one phase into another phase can also happen in the gas phase. And while growing nanoparticles in liquids is one of the most scalable methods for certain materials, there are also ways to make nanoparticles in the gas phase. And this is a schematic of a method where, for example, you would have a vacuum chamber, so at a low pressure, and you say, for example, have two sources of a solid material, and this is analogous to the syringe of precursor on the previous slide, and you would evaporate the material into the gas phase such that you can then condense it or collect it on, for example, a surface which is cooled. And depending on how much of this source you evaporate, you may create a sufficient pressure of the vapor of this solid material in the gas phase to nucleate the structures in the gas phase, or you may just deposit this and then deposit it down, or you may just deposit on this cold surface and then have the sizes of the structures grow with time there. And this is showing, for example, a case where you then move this cold piece, often called the cold finger, up and down, and you actually scrape the particles off, and then there's a way to collect them down there. So this is an effective apparatus where, by a general method of creating a vapor, understanding the nucleation of that vapor material and its deposition on the solid surface, you can create particles of a whole bunch of different types of materials, albeit it's a very low throughput apparatus, because you could imagine if you're just creating a few layers of these little particles on a cylinder, you don't get a lot of material at a time. So something that's a bulk method that takes advantage of a volume of a liquid or a volume of a very large reactor might be quite more scalable. Now, these are just two very basic methods of using this nucleation and growth process to synthesize populations of nanoparticle structures of, say, metals or ceramics or semiconductors, depending on what your precursor is or depending on what your source is for evaporation. And the previous slide takes some inspiration from typical methods of thin film deposition and growth. So things that are used, for example, in semiconductor fabrication to deposit films of oxides or nitrides, which are then, for example, patterned by lithography and used for device fabrication. So in another case, instead of having a cold surface on which you collected the nanoparticles that formed in the gas phase, you may, for example, have the same kind of crucible of material and have silicon wafers up on the top here and want to deposit the structures that you make onto flat substrates, and then you could grow them on those substrates and process them in different ways and shapes that we'll talk about later. And that precursor could be heated, for example, resistively. You could just have a hot wire and pass a current through that wire and melt the material like so, such that it evaporates above and then will condense on the cooler surfaces that are farther from this heated source. Or there are other methods, for example, such as sputtering, where you use an applied electric field. It can be a DC field or an AC field, and also you can use a magnetic field to try to drive the atoms of your precursor here toward a substrate. And I'm mentioning this because the evolution of a thin film as you deposit a material on a surface is essentially a nanoscale growth process. But now, back in the day, before we started thinking a lot about growth of nanotubes and nanowires and nanoparticles, we were more so wanting to grow films that were of thicknesses of, say, 100 nanometers or a micron. But now that the size scales of top-down fabrication are going, truly, say, to the tens of nanometer scale, and now that we're more interested in nanostructures such as nanoparticles, tubes, and wires, we're trying to understand how to control the growth of thin films within these smaller size scale regimes. And in general, the structure of the film that you end up getting on the substrate is going to depend on all the deposition parameters that you might have. The vapor pressure of your precursor in this atmosphere, the temperature of the substrate, the pressure of the chamber, and so on. And back in the day, in terms of studies of thin film growth, there's a lot of relationship developed between the process conditions and the structure of the film. For example, analogous to bulk materials, there's a lot of understanding of how the process conditions might change the grain structure of the film, whether you have straight grains through the film or you have disconnected grains through the thickness. And this has direct implications for the electrical properties, the thermal properties, and the mechanical properties of the film in a lot of ways that we talked about, transport and scattering. But when we think about synthesis at the nanoscale, we want to think about specifically how the atoms that come from this precursor phase deposit on the substrate and form the initial nuclei of the surface. And if we go for a long time, we might get one of the types of thicker films that we schematically saw here. But if we control the process for a short time, we might make these isolated small islands that can be considered nanostructures and then can be quantum dots on the surface, or can be catalysts or sites for growth of subsequent structures. So if we think in a vapor process, if we have a substrate on which the material deposits, what the fundamental processes are, we can have atoms coming out of the gas phase and depositing onto the substrate, and then the atoms can either say move, diffuse across the substrate, and collect in a particular place and form a nucleus, or they can say deposit and desorb, adsorb and desorb, or they can deposit and transport or diffuse and then desorb as well. And just as we thought in the gas phase in the room here of passing this critical concentration of precursor, the same thing can happen on the surface. If you don't have enough of the precursor atoms in the atmosphere, most of the atoms will come down and they'll have enough time to move around and desorb before you really get anything. But if you have a higher concentration of the precursor, or for example, if you have a higher probability of sticking this atom to the surface, meaning it stays for a longer time, then there are probably places on the substrate where you'll start to form these islands, and you'll start to essentially build nanostructures on a surface. And this is a direct analogy to the case of doing it in the gas phase, only now doing it on the surface of the substrate. And the kinetics of these individual processes of adsorption and sticking and diffusion and desorption determine the kinetics, the nucleation and growth process of materials on substrates, and are essentially the initial stages of growing a film, which are in many ways the ways that you grow nanostructures on a surface. And in the field of thin films, there are different models and mechanisms by which these films grow, and these are the things that you might see if you took a course on thin film deposition and kinetics. And it just shows that the way that you control the process and how the atoms of this material interact with the substrate, back to the basic principles of surface energy and interaction, determine how these islands grow. For example, if you end up forming isolated islands and then they get larger and larger and larger with time, or if it's more favorable if the material that you're depositing wets the substrate better, if you start to form layers that fully cover the substrate and then cover each other one after the other. And all these kind of basic atom addition processes are important to understanding how these structures evolve step by step. And for example, here are some pictures of formation, nucleation and growth of a thin film, and this is a case of silver on a single crystal salt substrate. Done because they wanted to study the interactions between the salt crystal and the silver. And here are plots or images of the deposition process versus time when the film is, quote, different thicknesses. So this is a case where if you were monitoring their thickness, you could say the average thickness of the film is 25 angstroms or 2.5 nanometers. But you don't have a uniform film here. You have individual islands of the silver material on the substrate. And you can see with time, as more atoms hit the substrate, you end up depositing into larger clusters, and the clusters can also lose atoms to one another based on their own energetic stability and their own size, and you eventually get a film that is more or less continuous. And with time, you would evolve that grain structure in the film that would then be going from what the size regime we're interested in to the size regime of continuous films. And I'm just showing you this not to bring the discussion of bigger thin film growth into our material, but to try to bridge the gap between what was done before and what's being done now by understanding the kinetics of how these structures evolve. And try to also draw some parallels between ways we'll talk about how nanotubes and nanowires grow and the simple model of nucleation and growth that we're going to build for the case of nanoparticle synthesis. And one of the specific examples of how this process of nucleation and growth on a substrate is directly relevant to the growth of nanowires and nanotubes is in a process known as, which has become called as vapor solid growth. And what happens is if you have a substrate sitting inside a vapor atmosphere, and this is ends up being a picture of a zinc oxide nanowire, which we'll see on the next slide can be made by this method, and you expose the substrate to a vapor of the desired precursor atoms. So in this case, it can be zinc in an atmosphere of oxygen. These basic processes of atoms adsorbing on the substrate, diffusing across the substrate, and desorbing on the substrate happens. And over time, the atoms start collecting in certain areas of the substrate. And in fact, if you have, substrates aren't often perfectly smooth, there are places that are little bits of roughness or little cavities. And because the energy change is greater if the atoms stick in a corner like so or stick in a little divot like so, you'll find that at locations that are rough, you end up forming clusters and the atoms collect. They might stick for a longer time, and therefore if you have a condition where you surpass this critical threshold for nucleation, you end up forming clusters on the surface. So if I, for example, stop the picture here, I would have this picture that I just had on the previous slide, a flat substrate or a substrate that looks flat from the top with a whole bunch of clusters of different sizes. And then I would have nanoparticles on a substrate. But what happens in this case is for certain materials, if I continue the process and I have a material that has a crystal structure that will grow more favorably in one direction than the other, and I control the pressure and the temperature of the process to enable the growth to happen slowly, I might indeed form nanowires of that material from the substrate upward. And this is what's referred to as the vapor solid growth process, and it was first spotted about 50 or 60 years ago by researchers who were studying the growth of tin from the gas phase. They had a liquid tin source in a vacuum chamber and saw growth of these whiskers and wondered why they were growing elongated rather than growing in the case of a film. And a classic example of this is zinc oxide, and because zinc oxide has an anisotropic crystal structure, it grows in a particular direction because you lower the surface energy more by adding atoms on the tip of the wire. And it turns out that after you go from this nanoparticle regime to, say, the nanowire regime, the same things happen, but atoms actually can hit the substrate and can diffuse all the way along the wire and incorporate at the tips, or they can go directly from the gas phase to the tip of the wire. And so that's one example, which is kind of a crossover regime between growth of a film and growth of nanoparticles and growth of nanowires, all following this basic process from which you start with a gas phase precursor and you control the conditions so you nucleate and you grow the material. And you understand how the materials stick and transport and unstick. And here is an example of how it's done for the case of making zinc oxide nanowires. In this case, you have a tube furnace, so it's you could example a quartz tube that has sealed caps at the end, and it's sitting inside a box with heating coils, so you can maintain a high temperature inside this tube. And you can also, because the tube is sealed, fill it with a gas, an inert gas such as argon. And the temperature of this process might be, for example, as high as 1000 C. And this temperature, if you have a powder of zinc oxide in the furnace, you can sublime this powder and you can create a vapor consisting of zinc and oxygen. And then if you have a substrate downstream of the furnace at a lower temperature where the vapor that you've created here becomes now supersaturated, you can then condense the zinc and the oxygen onto the surface and execute the process we just saw on the previous slide. And it turns out that by that process, you can deposit zinc oxide wires that have this specific orientation. They always grow along a certain axis dictated by the surface energy of the system. And you can do this in some cases without a catalyst, so just by this vapor-solid condensation method. And you can also do it using a catalyst, as we'll see later, or having a specific nanoparticle which has a higher affinity for what's coming out of the gas phase and then more specifically dictates the location at which the nanowire grows. And this leads us to the general process of chemical vapor deposition, which is used widely in thin film deposition or thin film methods as well. And in this case, you have, for example, a tube furnace or a hot atmosphere, which is filled with a gas, and you have a substrate on which you want to generally perform a surface process or a surface reaction. And I'm showing you this to extend the idea of depositing something from the gas phase, so just having our precursor atoms and bringing them together and forming the nucleus, to having a more complex atmosphere where maybe a chemical reaction will happen on the surface and then form a resultant structure. Or a catalyst will be involved and your precursor will dissolve and interact at that catalyst, and then a structure will be produced. So in these general processes, you have the transport of the reactants down the tube or down the furnace. They will diffuse through the narrow boundary layer in a fluid mechanics sense to the substrate. The reactants will then stick on the substrate, and a surface process will happen. The reactants might stick, might unstick, might stick, and then move. And maybe a reaction will occur where, for example, you could, say if this were ammonia or something, the nitrogen might react on the surface, and you might then lose a reaction product out the other end. And how those molecules evolve on the surface is another way that nanostructures can be grown and another way that thin films can be deposited. And all these parameters are important when you consider how to grow particular structures by this method. So this can be a large-scale furnace. For example, in production, you may have a silicon wafer that's of large diameter, and you'll have a tube at low pressure, and the design of this system to give uniform gas flows and the right pressure and so on is very important. And in the case of a lab scale setup, this is a picture of just a small tube furnace that can be used for nanotube and nanowire growth by a lot of the methods we'll discuss, where, for example, you would have the precursors in pressurized gas tanks. You would have a set of flow controllers to control the flow rates of the different precursors. And this would be a picture of the tube apparatus where the substrate is. And this being a schematic of what's going on here shows that you might have a small piece of a substrate, such as a square centimeter piece of a silicon wafer, and it would be sitting in this hot sealed atmosphere where these heater coils determine the temperature and where the sealed tube determines the gas flow. And you would execute a program of chemistry and pressure and temperature to get the process that you want to happen. So if, for example, we were operating in the first case where we had a vapor of a metal, we could, for example, deposit the metal on the substrate. Or in the second case where we had a chemical reaction we wanted to happen on the surface, we could bring in some precursors. They could react at the surface with whatever's there. Maybe we would form nanoparticles. Maybe we'd grow nanotubes and nanowires. And then you would have the products on the substrate and the things that are left over from the reaction, and they would issue out the opposite side. And in some of these cases, we may, for example, start with particles on the surface, which can be formed by that initial film deposition process, and then introduce a precursor. For example, in the case of growing carbon nanotubes, this precursor could be, say, methane or acetylene or ethylene. And because of the way the precursor interacts with these catalyst particles, the atoms may attach, migrate, diffuse, and detach, and also flow away in a way that is favorable for interaction to grow this structure. And I want to keep this picture general for now, of occupying the basic process of bringing the reactant to the site, adsorbing it, diffusing it, migrating it, and producing the structure. And later we'll see more details of how this actually happens. And as we saw before, there are cases where we can grow just one structure from one particle, and there are also cases, and for example, where lithography can be used to arrange particles or to pattern thin films which form particles, where we can then grow large assemblies of these structures at once. But the growth process here is essentially proceeding at the atomic level and relying on the fundamental interaction between the precursor and the substrate and the catalyst, and how it then organizes to build this nanotube at the atomic level. And for example, how well we control the sizes of these individual particles determines roughly the diameters of the nanotubes that are made. And for example, how the particles evolve with time as the growth process proceeds. For example, you might lose a bit of material by evaporation of the catalyst, or some of the catalyst might diffuse into the substrate and the particle will shrink, may, for example, cause the size of the structure to change versus time. So in all these cases, all these considerations are important, and we'll see how the conditions relate to the size of the structures and the evolution of the size of the structures with time. And for example, we could start from a thin film of metal, and we could heat that film to form the particles that we want to grow the nanostructures before the nanotubes are grown, and then we would end up with all the seeds that could then catalytically form the nanotubes by the CVD process. So these are just some example pictures of a typical process that's used to make nanotubes. For example, we start out with a silicon wafer and deposit a stack of thin films, a layer of alumina that's about 10 nanometers thick, and a layer of iron that's about 1 nanometer thick. And then when we anneal that in hydrogen, it basically changes the surface energy between the iron and the alumina, and we go from having a thin film of iron to having particles on the substrate. And then if we, after this step of annealing it in hydrogen, introduce the precursor gas, such as ethylene, for growing the nanotubes, we can then grow the nanotube forest upward like so. And for example, if we keep the substrate in hydrogen for a longer time, we would see that the particles will evolve in size. They will get larger because of diffusion from the smaller particles to the larger particles, and also because of the permeability of the substrate, you'll also lose some material with time. So later we'll get to see how this kind of relates to how the sizes of the nanotubes will change versus time, and how the density of the film might change as the growth process proceeds. But here we have a case where the basic technology of depositing of a thin film, understanding how the thin film material wets the substrate, and then how the precursor would come in and grow the nanotubes from these nanoparticles, all those steps are important for then producing the final film of nanostructures that we want. And what we can see is that we can start to build a picture of how these catalyst particles that will grow nanotubes or grow nanowires in general are kind of like small substrates and small reactors in and of themselves. So at the top left here, we have a picture that looks like what we saw at the start with a flat substrate where atoms hit the substrate and diffused and added or moved away. And the same thing happens on the surface of the metal particle, which can then lead to growth of a nanowire or a nanotube. And a precursor, in this case, we see a schematic example for acetylene or C2H2, with these being the carbons and the small ones being the hydrogens, can desorb and can absorb and can dissociate, and then can incorporate itself into the growing structure of the nanotube. And the reason why the catalyst is used is because the catalyst is essentially lowering the activation energy or the activation barrier for this process. It's favorable for hydrocarbons to adsorb to the surface of certain materials, and then it's favorable for them to diffuse over the surface of and or into the material, and then to precipitate out from the structure. And you have many steps involved in this process, and here it's just represented by a kind of a resistor diagram where you have transport of the precursor in the gas phase to the structure, you have dissociation on the surface of the structure, you have diffusion in the bulk of the particle and also on the surface of the particle, and then you have the precipitation of the precursor out of the particle to produce the final structure. So you have the same kinds of steps that we previously saw were involved for a thin film when you think about how to grow an individual structure, or how the growth of individual structures happens simultaneously to create, for example, a film of nanostructures like a forest of nanotubes. And the same kind of idea that we had for growing nanoparticles in the gas phase, crossing a nucleation threshold to start to form the initial particles and then growing the particles, actually happens in an individual nanoparticle when something like a nanotube grows. Because when you start out with the particle on the substrate, before you've started to grow the nanotube, you have to saturate that particle with carbon, or in the case of a gold particle for growing a silicon nanowire, you have to saturate it with silicon and then cause a phase segregation, and then you can precipitate out the structure, and then the structure can proceed and grow. So these are just some pictures from a model that was designed to capture the diffusion of carbon and iron for nanotube growth. And what this study demonstrated computationally is that with time, when you start out with an iron particle to grow a carbon nanotube, you first dissolve carbon into the particle, and then you reach a supersaturation of carbon in the particle, and then when it becomes supersaturated, you start precipitating out carbon from the surface. But the carbon reorganizes in a crystalline graphitic network, and then the growth of the nanotube proceeds after you cross that critical threshold for nucleation. So we're seeing here how we can treat the particle for growth of an individual nanotube in the same qualitative way that we're going to treat a whole reactor for growing a large number of nanostructures or a large number of nanoparticles in parallel. And as we've seen before, and we'll see more later, depending on the size of the particle, you might get a single-walled nanotube, or you might get a multi-walled nanotube where you have one structure in the center and another wall on the outside. And if this were bigger, you might have many, many more concentric walls. And because of the limitations of this computational method, there were a lot of defects in this structure. This is not meant to predict the exact final configuration, but to show the dynamics of the process of diffusion, supersaturation, and then nucleation that happens when this structure is formed. And the details of what's happening at the interface are also important, and where our understanding of this process is now is how the atoms are actually incorporated in the nanostructures as they grow. So for example, here is a picture from an in situ TEM study of a silicon nanowire growing from a catalyst particle which is made out of palladium. And this paper discusses how the silicon precursor comes from silane, SiH4, and the silane loses silicon into the particle, and once this particle becomes supersaturated, you have diffusion of silicon, represented by this JSI, in the particle into this interface, and you have diffusion of palladium away from the interface, and the nanowire actually grows by this ledge flow method, where you form layers of atoms of silicon that move across and across and across and across sequentially, and you build the nanowire one layer at a time. And you have to cross a nucleation threshold every time a new layer is created, and then it grows, and then another layer nucleates, and the next layer grows across. And in the case of carbon nanotubes, what's being seen in most recent studies at the atomic level of the process is that atomic steps between the catalyst nanoparticle and the structure are important in essentially attaching the carbon to the particle. So here is a picture taken in the TEM of single-wall nanotubes that are the initial stages of the process, and here you see a picture of this initial cap kind of lifting off, and then the cap getting longer and starting to produce the structure. And as time goes on, this indeed straightens out, but what you can imagine here is that the shape of this structure and the details of the physical interactions, the configuration of the atoms of this particle with respect to the lattice that's forming, are really important for controlling the characteristics of the structure. And in general, when we think about all these processes, there are always a large number of variables, depending on whether you're starting with just a regular gas phase nucleation process, and you might just have the vapor pressure of the precursor and the saturation vapor pressure and the pressure and the temperature, or if you have the multi-step process of making catalyst and growing nanotubes, there are a lot of parameters that are important. So, we can see that the type and the size and the chemical state of the catalyst and all the kind of reaction conditions and flow dynamics and so on will be important. And our goal is to relate these characteristics at a basic level to the outputs of the structure that we have. How do we control these variables to control the diameter and the structure of the nanotubes? And how do we think about how they lengthen with time, how fast they grow, how long they will grow before the process stops, and how that relates to the defect density and the characteristics that govern the functional properties. And I think, in a long time, what we ideally want to have is an ability to model the growth of one nanostructure and understand how these conditions relate to the outputs and the characteristics, and use that to develop methods to control the growth of large numbers of structures. How can we take a model for one structure and multiply it many times, or convolve it with a size distribution that we know to be, and then predict what our bulk material will be in the end, or how many of our devices, how many of our individual wires will have the appropriate characteristics to grow the structure in the last place. And as we saw from the previous slides that showed the atomic model and showed the examination of the interface, our ability to model the growth of one structure is still really at an infancy. There are a lot of places in which we don't understand how the atoms are really incorporated in the structure. And we're maybe able to say that if you have an iron particle of 1 nanometer diameter, you get a 1 nanometer diameter nanotube, say plus or minus 0.1 or 0.2 nanometers. But we don't understand, for example, why the nanotube has one chirality versus another chirality. And this connection is bound to improve over a few more years of research. So what I wanted to do and what we've covered so far today is kind of give a broad overview of the types and implications for making nanostructures, specifically nanoparticles, nanotubes, and nanowires, by different methods. And I realized that was kind of a whirlwind and was probably bringing in some ideas that will become clearer later, but I wanted to do that so we can now talk about this basic process of nucleation and growth with the mindset that it's important to a lot of different systems. And we can break down the idea of starting from zero and adding material atom by atom with this basic model. And if we think back to what was happening in the different processes we already discussed, we could break down the types of nucleation into 3 different categories. There's what's called homogeneous nucleation, where we have one material and 2 phases. So for example, we could have a liquid phase and we could make solid particles, or we could have a gas phase and we can make liquid particles, or a gas phase and make solid particles. So we nucleate one material in the presence of only itself as the medium. We could also have a case of what's called heterogeneous nucleation, which means, in one example, that we're forming a nucleus of a material on the surface of something else. So that term would be used, for example, for growing the zinc oxide nanoparticles or nanowires on the surface of, say, an alumina surface or a gold surface, or, for example, growing carbon nanotubes from an iron surface. And then we can also have what's called secondary nucleation, where we start out with seeds of existing structures and we add to those seeds. So in some cases you could grow nanostructures by making nuclei in one way and then introducing them to another system and making them bigger, or using one particle as a seed for another particle. So in the case of types of nucleation in material science, we can classify processes into these 3 different categories. And that may determine, for example, whether the surface energies of different materials are important, or just a phase transition from one material to another is important. And now what we're going to do is we're going to talk about in detail the first case, where we're going to think about quantitatively how we would nucleate one material from another phase of the same material. Or imagine that we're sitting inside this room and we fill it with a pressure of a certain precursor, and we want to change the conditions, so we go from this slide being blank to having all the small blue dots on it, to creating nuclei of one material inside another phase. So So let's imagine that we have a container that's filled with two phases. Say the first phase is a vapor, and we want to study what the conditions are for formation of another phase, liquid droplets within it. So, this can be, say, it could be a container filled with water vapor where we're getting little liquid droplets, or it could be a container filled with metal vapor where we're getting droplets of that liquid metal. And we're going to derive, for example, the total change in free energy, delta G total, that's needed to form one particle. And we can say that this is kind of like we had for melting of particles. This is a bulk energy change plus a surface energy change. And now we can equate the bulk energy change to an expression for the number of atoms in our nucleus, and we're going to assume that it's a spherical particle. So this expression is a relationship for the number of atoms, n, or the volume of the particle, assuming that it's a sphere, and the volume per atom, or the atomic volume, and the change in chemical potential, or total internal energy, per atom, upon phase change from the vapor to the liquid. So this is our bulk term. And then if we look at our surface term, we are going from no droplet to a droplet. So we need to create a surface which has the surface area of a sphere. And we can say that our surface term is just added here, and this is the surface area of the sphere times the surface energy, gamma, because we're creating a surface with a certain surface energy, kind of as we saw later. So if we look at the bulk term in more detail, we can say that we defined it as the number of atoms, n, multiplied by the change in chemical potential, mu, which we can say is n times the chemical potential of the final state minus the initial state. And we're going to define that this can be equal to a relationship which relates the temperature and the pressure of the system to the chemical potential. And this is assuming that we have an ideal vapor, or essentially an ideal gas of our precursor in the system. And so we'll say that this is equal to minus n times the thermal energy, Boltzmann's constant times temperature, multiplied by the natural log of a parameter s, where we define s as the supersaturation, or the vapor pressure of our precursor in the system, divided by the equilibrium vapor pressure of the precursor at that certain temperature. So, equilibrium vapor pressure is the idea of if you have a liquid at a certain temperature and you have a gas above it, the equilibrium vapor pressure is the pressure of vapor that would be existing above that liquid when the vapor is in equilibrium with the liquid. So you're not condensing or evaporating, you just have equilibrium exchange. And the idea here is that if we control the conditions so we supersaturate the atmosphere, so we have more vapor than there should be in equilibrium, then it'll be energetically favorable for the vapor to condense into droplets or condense into clusters and for us to start forming nanostructures. And the same thing can be applied qualitatively to having them in the gas phase or having them on a surface, where we're now, instead of saturating the gas phase with precursors, we're saturating the surface with precursors, and we're starting to form clusters. Or we are not talking about a bulk surface with a whole bunch of clusters, but we're starting to saturate an individual nanoparticle with precursor that will then start spitting out a nanotube, spitting out that cap or that nucleus or that head of a nanowire when the particle becomes too saturated and has more than the equilibrium state. And this general dynamic of crossing an energy barrier or crossing an energetic threshold is the fundamental event which starts a nanostructure being built from the bottom up. So if we look at these terms in a bit more detail, we have our bulk term, which we have related now to the number of atoms and the supersaturation of the atmosphere. So essentially pressure and temperature, which are the kind of conditions we want to talk about, because those are things we can control. And now if we look at the surface term, all we want to do here is we want to redefine it in terms of the number of atoms in the system, because then we can move forward with both terms in terms of the number of atoms. So we had the surface energy term is 4 pi r squared times the surface energy gamma. And what we need is a relationship between the total surface energy term and the number of atoms in the system. So we can say that the volume of the particle is 4/3 pi r cubed, which is equal to the atomic volume times the number of atoms. And if we used this to build a relationship between R and the number of atoms of the system, we could then say that 4 pi r squared, we won't go through the steps, is equal to the quantity 4 pi times 3 times the atomic volume divided by 4 pi to the 2/3 multiplied by the total number of atoms to the 2/3. So now our total expression for the free energy change delta G is equal to our expression for the bulk change in energy in terms of the supersaturation plus the surface energy gamma times 4 pi times the constant which relates to the atomic volume of the material we're working with multiplied by the power of n to the 2/3. So because surface area is r squared and volume is r cubed, our surface area term is going to be related to the number of atoms to the 2/3. So if we want to figure out what the critical cluster size is for nucleation, can someone say what we will do with this expression? Basically, what is the cluster size that is going to keep growing versus the cluster size that's going to shrink and is not going to be stable?
To 0?
Exactly. So we're going to take the first derivative of this expression and we're going to set it equal to 0, and we're going to determine the critical number of atoms n star, which is our critical cluster size. And for example, if we plotted this expression delta G versus n, we would see that, like we had for melting in a way, it's a parabola with a maximum point where the first derivative of delta G with n, the number of atoms in the system, is equal to 0. And that means that if we have a cluster that's smaller than our critical size n star, it is going to shrink. And if we have a cluster that's bigger than our size n star, it is going to grow. Basically, each particle is like a little system that wants to decrease its free energy, delta G, which is on the vertical axis. And if it is on this side, then it'll decrease its energy by shrinking. And if it's on this side, it'll decrease its free energy by growing. And so we have to provide enough energy to the system to cross this critical nucleation barrier, have enough temperature or enough pressure to form these nuclei, so they then form and then will want to get bigger, rather than form and disappear and end up in our initial state. So if we take the first derivative of our initial expression and set it to 0, we would lose the n from the first term, and then we would end up with an n to the minus 1/3 on the second term. So we'd get that this is equal to minus kBt times the natural log of the supersaturation, plus we then have 2/3 multiplied by 4 out front, so 8/3 pi times gamma. And our atomic volume term doesn't change because it's just a constant, multiplied by n to the 1/3. Yep, that's right. Thanks. That should be an 8. And if we solve this for n, we'll get that the critical cluster size is related to the surface energy in the numerator and the temperature and the supersaturation in the denominator. Sorry, I want to insert another slide here. And for example, if we use the relationship between R and N to convert N star to a critical radius, then we would get that the critical cluster size in terms of radius is twice times the surface energy times the atomic volume divided by kT times the natural log of the supersaturation. So this tells us that if the supersaturation increases, or for example, we go back to the initial picture from today and add precursor to our solution, then we increase the supersaturation, then the critical cluster size is going to decrease. And if we increase the temperature, then likewise, the critical cluster size is going to decrease. So supersaturating the system and or increasing the amount of precursor is a way to initiate nucleation, is a way to cross this energetic threshold and start structures synthesizing. And ideally what we want to do is, for example, going back to the first picture, we want to start the process by adding that precursor, by rapidly increasing the temperature. And then once we form the nuclei, we want to step back into a regime where we already have clusters that are above the critical size, so they're not going to dissolve, but they still want to grow to decrease their free energy. And next time we're going to see the next picture of the process. Now that we form these nuclei, how do these nuclei grow and how do their size distributions evolve? Because, as you can imagine, this ideal picture gives us a general case of what's going on, but there are local fluctuations in the system, and not every cluster is going to have the same size, and therefore you're going to have locally different processes and dynamics depending on where you are and what the chances of a particle being a certain size actually are. And these calculations can be done for values for practical materials. In this case, it's done for assuming you're condensing metal clusters from the gas phase. And this just shows, for example, critical cluster sizes being in the order of tens of atoms. So things that are substantially smaller than 1 nanometer being the sizes of vapor clusters that you'd form under particular conditions. I think this was a case where you had a background pressure of about a half torr, and you had an equilibrium vapor pressure of, say, 0.01 torr. So here, the supersaturation is about 50. And for aluminum, this would be, for example, at a temperature of about 1472 Kelvin. So that would mean that you'd have a very hot atmosphere, you would have a very hot crucible of aluminum, and you'd be creating this vapor, and then you would have a pressure of a real pressure of 0.5 torr and an equilibrium pressure of about 0.01 torr. And taking from this idea of nucleation to start the process, to bring us back to the start, this is exactly how we start to think about how the size distributions of nanoparticles evolve in solution by, for example, controlling the temperature versus time or controlling the amount of precursor versus time. And as we saw before, we can use transmission electron microscope to quantify the size distribution of the clusters that are formed in solution. So this is in fact a case where they took some of the solution and deposited on a grid for TEM, and because of the capillary interactions that we'll learn about later, the particles deposited into a well-defined monolayer. And this was a way of examining the sizes of the structures after the process. But what these researchers actually did, and this is from the Peng paper that's up on CTools, is they used the relationship between the optical properties of the crystals and their size to monitor the size, the average size of the clusters or the nanoparticles in solution versus time. And the different curves here represent the absorption spectra of the particles at different times in the synthesis process. So here we have 0.2 minutes. So right at the nucleation process, the particles emerge, and then many minutes up to several hours after, and you can see that the energy of emission is decreasing with time, which means that the particles are getting bigger. So there you can see you can monitor the absorption spectrum and the photoluminescence emission spectrum. And if you know the relationship, just the basic model we had in terms of band gap, it's possible to monitor the size of the structures versus time. And what the paper showed is how the synthesis conditions, the temperature and the concentration of precursor, relate to the average size of the structures versus time and the standard deviation or the size distribution of the structures versus time. And the arrows in these plots here indicate the times at which they injected precursor to the system. So the first arrow here, and these are they studied 2 different materials, and we'll just concern ourselves with the first material, cadmium selenide. They injected precursor into the system, and particles formed very rapidly. You went up to a size of, say, between 3 and 4 nanometers within a matter of a few minutes. And in the initial stages, before the nucleation happens, you can't really define the standard deviation, but you formed a relatively monodispersed population of particles. So these particles that were about 3 nanometers in size had a fairly low standard deviation of maybe about 10%. And then what happened as the particles grew and kept consuming the precursor from the solution is that the standard deviation started to broaden, and so the particles distribution got broader. And then later on, what they did is they injected more precursor into the solution, not to cross the nucleation threshold again, but to change the dynamics of the process so the conditions would dictate that the size distribution then started to focus. And so while today we maybe understand a bit about what happens here when we inject this initial precursor and create the nuclei cross this critical threshold, where we'll pick up next time is what happens here when they use a further injection of precursor to then control the size distribution to focus it down in the end. And it turns out that what we saw in the TM is in fact a fantastic result, a very highly monodisperse distribution of structures which gives those very pure optical properties. And ideally we might want to have them atomically precise, but getting down to the levels of standard deviation being a few percent of the diameter is a very good result that is enabled by understanding of these nucleation and growth dynamics. So that's where we will pick up next time.